Hi, everyone. This is Chen. I'm a PhD student in Vision Care Group. Today, I'm very excited to share my research work with you guys, which is VisualGPT, data efficient adaptation of pre-trained language model for image captioning. Firstly, I'm going to describe the motivation of this paper. In the past few years, we have witnessed a lot of giant pre-trained language models in natural language understanding domain. For example, BERT and GPT and XL9. Those pre-trained language model has accumulated a lot of human knowledge. Image captioning is one of the most popular research topics for image content understanding. So how to effectively leverage the language model knowledge on image caption task remains a big research question. And this is our research focus. This is our overall model structure. It follows the transformer setting in general. We firstly deploy the fast SAN to detect the sequence of bounding boxes and feed them into the visual encoder. And we rely on the GPT model to generate the image content description. And we also design the novel encoder-decoder attention to link between the encoder and GPT model. Compared to other similar transformer decoders, basically, they all have very similar architectures, and they have same components like masquerade self-attention and feed-forward layer. The main difference is that they have different encoder-decoder attention and also the pre-trained weights. For example, vanilla transformer only has a simple cross attention, and the attention on attention net, like they has attention on attention on top of self-attention. M2 transformer, they deploy the matched connection and have all the encoding layers output into consideration. In our case, we design a novel encoder-decoder attention to balance between the visual input and the GPT weights. Let me describe our encoder in more details. The main novel part is that we design two attention gates, which is beta visual and beta language, to attentively balance between visual input and GPT weights. When we calculate the beta visual and beta language, so as you can see here, we have the predefined threshold tau to define the liveness of activated attention values. If the attention values is lower than the threshold, it will become dead status. If the activation value is between tau and 1 minus tau, beta visual and beta language are complementary to each other. Such design can allow the model to decide if it is going to condition on visual features or language features while generating the next token. Here are our experimental results. We demonstrated that our VisualGPT is more superior when it is in the data efficient setting. We train our model on 0.1%, 0.5%, and 1% COCO training data. Our VisualGPT is much better than the best baseline models. In the similar setting of conceptual captions, our VisualGPT also outperforms other baselines. Our VisualGPT also achieves the state-of-the-art performance on X-ray medical report generation problem. Through extensive evaluation study, we also found that our encoder-decoder attention is much better than other encoder-decoder attentions, like in vanilla transformer, attention on attention, and also M2 transformer. Thank you for watching the video.